Okay, folks, let's try and frame where we are with everything. Unit 1 was essentially a review of 11U with a couple little add-ons, a couple of things that were not finished off in 11U. Unit 2 finally added a new weapon, and it was a big weapon. It was rates of change. Average rate of change and instantaneous rate of change. And some graphs in there, but the big idea was average rate of change and instantaneous rate of change. So now we're going to rewind back the clock and get our momentum going that we had before 11U came along, and basically you did an algebra course, essentially. In grade 9, you were doing y equals mx plus b. Graphs of lines. Essentially, only x's and numbers. I'm going to review that within this lesson. Then in grade 10, you added y equals x squared. You know, degree 2. What we mean by that is exponent 2. I'm going to talk about degree today. Well, things got out of hand for a while, didn't they? Things went nuts as soon as you went x squared. Factoring, complete the squares, zeros, x-intercepts, y-intercepts, quadratic formula. It took a while to nail down degree 2. But I got great news. Within this chapter, we'll handle degree 3, 4, 5, 6, 7, 8, 9, 10. All the other degrees of polynomials, we'll handle them in this chapter. What's nice about this lesson is it's sort of an intro to all that. It sort of frames all that. It sort of lengthens out what I just said and really frames where we're at with all this. We're going to try and nail all the polynomials now. And I say all the weapons are in place now. All the little pieces you need to analyze any polynomial you want is now in place. We can proceed. Now, this lesson is not particularly long and not particularly difficult. I'll review some words we need and an introduction to what we got to do in this chapter. So first we want to define what a polynomial in one variable is. And you've had a taste of what polynomials look like before. In fact, all the way into elementary school, I think they talked about what a polynomial was. But only now does it really come full circle where we can really talk about what a polynomial is. A polynomial is an expression of the form an x to the n, an minus 1 x to the n minus 1. Look, you can hear me laughing as I say it. I know what this looks like. It looks like a big mess. Let me start backwards. Look at those last two terms, a1x and a0. There's grade 9 right there. I know you called it mx plus b, but these are just different letters now. There's grade 9, y equals mx plus b. So that was one type of polynomial, mx plus b, degree 1, because it had exponent 1. Grade 10, now degree 2. Does that really look familiar now with what you talked about with quadratics? Except it was ax squared plus bx plus c. They're using all a's here because we're going to run out of letters. If we start going a, b, c, d, e, f, g, h, that's going to be crazy. So instead we go a2, a1, and a0. These are the symbols we use. Not getting too carried away with that in this lesson. All we're trying to say is now we're going to try and open up and do any kind of polynomial. Any x with whole number exponents and any coefficient. Actually, that's the first half of the lesson in a nutshell. My job to explain to you that polynomials means whole number exponents, 1s and 2s and 3s and 4s and 5s, but any coefficients you want. I did a test one on the board there. 2x to the 9th plus 7x 7th plus 3x cubed minus 2.5x squared plus 5x minus 1. Yeah, a crazy polynomial. Seems unattainable at this point, that we can't handle that at all. Well, I promise during this chapter we'll make it so we'll have a very specific set of steps. We will not be intimidated by upper degree polynomials by the time I'm done. One little step at a time though. Today we just talk about them. So a polynomial has all of these exponents as whole numbers. You won't see x to the power 2.5. You won't see root x. None of those things. Just whole numbers. And the coefficients can be any real number. So these coefficients that are out in front of the x's, well, they can be whatever you want. 2, 7, negative 9, 4.2, whatever coefficients you want there. We won't get crazy with the coefficients. This definition says the coefficients a0, a1, a2, an are real numbers. What's a real number? Well, a real number is any number you can think of right now. 2, 7.4, negative 3.8, pi. All these numbers that you've been using the whole time, those are the real numbers. Immediately you ask, well, is there not real numbers? And I think that mathematicians maybe are just being funny when they call them real numbers because it freaks people out. And they go, are there numbers that aren't real? And the answer is yeah. Sometimes they call them imaginary numbers, and people go, so you're just making up numbers? They're imaginary numbers? Maybe a better word for it would have been imagination numbers. You've got to use your imagination a little bit. You've got to be able to think a little bit to be able to work with imaginary numbers. But let's rewind a little bit to kindergarten. Let's say we went on a road trip to visit my son's kindergarten class. And I said, okay, kindergartens, tell me a number between 3 and 5. A whole bunch of hands would go up. They'd be very excited. They love to answer questions. And they'd say, oh, 4. 4 is a number between 3 and 5. And I'd go, yeah. And then I'd look at you and I'd go, watch this. And I'd say, okay, kindergartens, tell me a number between 3 and 4. And they'd say, they'd look at me like I was an idiot. That'd be the funny part, is they'd go, there's no numbers between 3 and 4. Where'd you get this guy from? He's an idiot. It goes 3, then it goes 4. That's the way the system works. And actually, I argue I am the idiot. Who would go in and ask a question like that of kindergartens? It doesn't make any sense. You would go in and you would start breaking things in half. You start talking about money, and you'd work your way up to the idea that there's a lot of numbers between 3 and 4. So do you see, in their number system, there's 3, then there's 4. That's the real numbers to them. That's what's real. Anything else is just made up garbage. Where are you getting this from? How long does it take to get decimals and fractions nailed down? Years, isn't it? Years of practice before decimals and fractions become something that's part of your real number system. And I'm playing with the definitions just a little bit, just to get you a feel for why the real number system isn't quite as tricky as you might think. Well, okay, that's where you're at. With the next step in numbers, the next kind of numbers, square root of negatives and these type of things, we need to take a year or a course or two and get to the point where we can understand where those numbers come from. It's not too bad, actually. If you're taking my AP Calculus class next year, you could do a project on it and explore complex numbers pretty easily, pretty quickly. Yeah. Okay, so don't be intimidated by real and imaginary numbers. Just know real numbers are everything we're used to, and this lesson doesn't go any farther than that, just to say, just the numbers you're used to. Don't get carried away here with anything. Review. If it's a polynomial, the exponents are whole numbers. If it's a polynomial, the coefficients can be any number you can think of. Negatives, fractions, decimals, whatever you like. Let's do for some examples. It really needs some examples here. Some examples. Here's some polynomials. A familiar polynomial, 3x squared minus 5x plus 3. This is a polynomial with degree 2. Because the highest exponent is 2. I'm already giving away the next slide. I'm talking about degrees already. This one, a polynomial with degree 7. The highest exponent is 7. Notice, all the exponents are like 7s and 4s and 1s, but the coefficients, negative 4, 5, negative 3, and 2, they can be positive or negative, and you find out in the next one. You can even have fractions as the coefficients, but not in the exponents. The exponents will all be whole numbers. You'll see why very soon. We want to be able to factor these things, and so we're going to use whole numbers. So and then when you see this, and you see root 4x cubed, you're like, well, I thought you said there's going to be no square roots. Well, the coefficients can be square roots. They can be decimals. They can be negatives. But the exponents, 3, 2, 1, the exponents will all be whole numbers. Those are all polynomials. This last one's a polynomial as well. You'd have to multiply all the brackets out to see the degrees and all that kind of thing, the information you want, but it's still a polynomial. Let's talk about these ones on the right. Maybe they're a little more instructive. Well, what's not a polynomial? Well, root x plus 5x cubed is not a polynomial because polynomials will not have roots in them. That would be an exponent of 1/2. So that's not an exponent that we'd see in a polynomial. This has a denominator, and anything time x is in the denominator, we're going to study those in Unit 5. We're going to talk about them. But while we're doing polynomials, that's not considered a polynomial. This sort of looks like a polynomial. 6x cubed, that's polynomial. 5x squared, that's polynomial. Negative 3x, still polynomial. 2, yep. 4x to the negative 1. Polynomials won't have negative exponents in them. Can we study negative exponents? Of course we can, but we just won't call them polynomials. Well, again, denominator, not a polynomial. Exponent of x up there, no. Whole number exponents only, not x's up there. That's an exponential, not a polynomial. Sine, no sine or cosine to be a polynomial. This one, negative power, and this one a 2.5 power. So those ones all break the rules of polynomials. Are there any questions about the rules of polynomials? So far, all I've said is Again, just to review it, all I've said is whole number powers and any coefficients you want. Note, a polynomial can use a variable other than x. I could use t's in my polynomial if I wanted, or n's, or whatever letter you want. A polynomial can contain more than one variable. Here's a polynomial with x's and t's, which again might freak you out. You go, how can you get a polynomial that has x's and t's? Well, the easiest example I can give, and we're not going to really do any of these, would be if I was trying to figure out how much traffic there was on the road and I was driving to Toronto. You can see x would matter. How close I was to Toronto would affect how much traffic there would be. You can imagine as you get close to Toronto, there'd be a lot of traffic. But time would also be a factor in the sense that if you go to Toronto at 3 a.m., traffic's not going to be a big deal. But if you go at 3 p.m., traffic's a huge deal. So you could imagine a function, a situation where x and t both matter, okay? These aren't not that difficult to work with, actually, weirdly. But we're not going to do any of that. We'll stick to polynomials of one variable only. Oh, some more words. I've already introduced this. I tried to lay the foundation for this. A degree of a polynomial is the value of the highest exponent on the variable. Here's an example. 7x cubed minus 12x squared plus 5x minus 8. A new polynomial to us. Up till now, we've only done x squareds. So now this is the new highest exponent, so that's the degree. Whatever the highest exponent is, that's the degree of the polynomial. That's how we'll talk about polynomials from now on. Y equals mx plus b, we'll often just call it degree 1. Y equals ax squared plus bx plus c, the quadratics, we'll often call those degree 2, and this is degree 3. Another new word, leading coefficient. The leading coefficient of a polynomial is the coefficient of the highest power of the variable. We'll do a lot of this tomorrow. We'll really focus on what's the highest exponent and what's its coefficient. That'll really affect what we're doing tomorrow. So, exponent 3 and the coefficient is 7, so that 7 is the leading coefficient. Doesn't have to be the first term, by the way, but you usually should be. You'll see an example coming up. Polynomial function. Well, a polynomial function is the same as these, except it's y equals or f at x equals. These are just expressions. They're not polynomial functions yet. Here's an example of a polynomial function. See, this is the expression 7x cubed minus 12x squared plus 5x minus 8. If I want to make it a function, I just put f at x out there. So not a big deal. That's a small terminology difference between what's going on here is that's now a polynomial function. All right, well, let's test where you're at. If we can get all these answers, you're in great shape. Even if some of that stuff sort of went past you, you're like, I'm not sure exactly what he meant there. Even if all that's true, all we really need from that part of the lesson is name the degree and the leading coefficient. What would the degree of this one be? 4, the highest exponent you see. And then the leading coefficient, once you've found the degree, the leading coefficient is just the number out front there, is negative 8. And in this lesson, it's like, why you care so much about the degree and the leading coefficient, and you find out more tomorrow. The degree and the leading coefficient is going to really help us to understand what this polynomial is all about. How about this one? Degree. Trying to fool you here on degree. What's the highest exponent? 4. You look through, who would write this like this? You know? You shouldn't write this like this. You should write the highest degree term first. But it could come up that you encounter a polynomial where it's written like this, but degree 4, and then leading coefficient. Is that weird? What's out front of the x to the power 4 there? 1. So the leading coefficient here is 1. One more. Highest degree, 7, 5, and 3. Highest degree is 7. And that leading coefficient then is negative 4.1. So don't be misled when it says leading coefficient. We don't mean the first coefficient you run into. We mean the coefficient with the highest exponent. And again, tomorrow it becomes very, very clear why that's so important to us. Questions? It is recording. That's the stop. When I want to stop. I'm recording it because I noticed the lesson online. The audio cut out, so I must have ran out of batteries the day I did it on my little cordless mic here. No, not really. Not really my problem if there's not a video there, is there? It's your problem. No, I like having a full library so when people are away, like, okay, the video is right there. And so anybody who's away today can just watch the video. But the video had an audio problem in it where it stopped having audio about the 17-minute mark, so I'm trying to redo it. Now you get to be on the video. You might. Generally not. Generally what you hear on the video is me pause, and maybe in the background you hear a sort of a, a little noise, and then I answer it. But generally speaking, you don't hear the voices of the people in class. Once the announcements came on, you could just barely hear the announcements in the background, but normally that's not a problem. You see, I'm not too formal about it either. I don't, it's the video. Whoever's watching this video sitting there going, can you just get on going? But that's why the fast forward thing is so good. You can fast forward to the next example and so on. Or just fast forward to the example you want. If you're having trouble with a certain homework question, you can zip through the video and find my explanation again, Examples of polynomial functions. Okay, actually I'm going to switch gears here. I'm going to do this whole chart using something called GeoGebra, which you can actually download on your phone and do many of the things you'll see GeoGebra do. I've got a fun little deal here. Let me switch to, and let's just do a review of the polynomial functions and a preview to the ones you're going to see this chapter. So I'll tell you when. There's stuff you should know, and then there's stuff that you won't know, but I'm going to introduce you to. Okay. Grade 9. Straight lines. Everything was straight lines. It seemed like the whole world was straight lines. And there was only two things that really could happen. Is one, you could change the y-intercept, and you could move this thing up and down. And you could change the slope, which you could change how much it goes up by. You could go positive, you could go negative, whatever you like. So that was degree 1 functions in a nutshell. Then we learned about degree 2 functions, which were called quadratics. And now there was more to the game. There was a coefficient out front which will allow you to stretch this thing or flip it over. But then there was coefficients that allowed you to move it around as well, up and down, left and right, wherever you wanted to go. So you had lots of options with a parabola. But let's just talk about it for a second. It actually wasn't that complicated. The end behavior was the same on both sides. You had some vertex somewhere. You could either open up or down and then just move the thing left or right. So as long as that took, there wasn't too many features to this. Start up, go down to a bottom, and then back up again. Or, well, I guess you could flip it over. Yeah, those are the only two options that were really available. And you can move it around all you want. Okay, now everything I do next you're not responsible for at the end of this period. Yeah? You're just an introduction to it so you can sort of see what's coming. It's not as scary as it looks. I'm going to give you, each day I'm going to give you a new weapon on how to deal with polynomials, and it'll get easier and easier as we go. So, cubic. Cubics can be shockingly similar. When you go to x cubed, are shockingly simple. When you go to x cubed, you can get a nice simple function like that. But based on how you change these coefficients, it could open up or down, or, it's not up or down, is it? It's switch its direction, or watch what happens. Just by playing with these numbers, you could get, instead of 1 max or min, like you do in quadratics, you could get 2. Actually, I'm giving away so much from tomorrow's lesson here now. You're learning lots about x cubed right now. What could happen? You now could get 2 max mins, and you could get 3 different zeros. Could. I say could because you saw when I put these down to 0, when the coefficients are simple numbers, this thing becomes pretty simple. It doesn't have to have all those features. And that's going to bother us a little bit because we're like, well, how am I going to know if it does have these features? I'm going to give away now the first Monday's lesson after March break. One of the key moves we'll do is just find the zeros. If we can find the zeros, we'll know a lot about the function. So that's we'll get to work on it. How are we going to find these zeros? And there's going to be nice ways to do it. So if we go to degree 4, it can be very simple. Sort of looks like a parabola, but things can get right nuts here. Let's check this out. I'm just going to play with the numbers here. That does that every once in a while, sorry. And then I can maybe flip it over, shall I? I'll go to negatives. Yeah, all sorts of possibilities with a degree 4. The big thing is it could get up to 3 maxes or mins and up to 4 zeros. So giving away tomorrow's lesson when I say that. But that's what you're going to see as you move along here. And then I'll do a degree 5. Same deal. You could start off with something simple, But things can get right nuts here. It's actually difficult to get all the features in one of these. Let me see if I can get something cool going here. Move that up. Yeah, lots of cool stuff that can happen with degree 5. Now, everything I just showed there, you're not responsible for today. I'm just giving an introduction to what could happen with these polynomials based on the coefficients, and obviously we've got a lot of work to do this chapter to figure out all these little things. But one step at a time. It's such a good chapter. Each day is just one little thing, and by the end of the chapter, we'll be able to knock down these things. Back to this chart, which I think I've totally done now. But I'll say it again, everything on here, but you saw my demonstration on that, and you can go back and watch that part of the video anytime along the way just to get to know what functions we'll see this chapter. Again, that's a preview to the chapter, not a whole bunch of stuff you should know. So degree 0 was the constant functions, y equals 3, y equals negative 5. So technically these are called degree 0. Those were just horizontal lines. Then degree 1 is the linear functions, y equals x, y equals negative 2x plus 5. These are the y equals mx plus b's. Here's a couple of samples of what lines might look like. Degree 2 is quadratic. Here's a couple of quadratics and what they might look like. That's all review. Everything else is preview. Not that you should know this stuff after I finish teaching today, but here's what we're going to look at this chapter. Degree 3 could be a cubic, it could be simple, or it could get pretty wild. You know, instead of one max like the quadratic has a max and a min. Isn't that neat? Degree 4, quartic, can be simple or it can be pretty complicated. You know, 3 max mins, maybe 4 zeros, maybe only 2 zeros. How are we going to know how many zeros? Oh, hey, that's what the chapter's all about. We're finding out how this can happen. And then degree 5 is called quintic, and can be fairly simple or really kind of wild, up to 5 zeros now, yeah? So, exciting stuff coming. You know, we're going to zip right through all the other degrees. 1 whole year on degree 1. Basically 2 years on degree 2. And then in one chapter, we're going to zip through all the other degrees. I've got 2 important weapons to give you. And once I give you those weapons, life's going to be pretty straightforward here. You're not going to be intimidated. On the test, if I say, here, graph this quartic, and I give you a quartic with coefficients, by the time the test comes, you're not going to be intimidated at all. You're going to be like, I'll do this, I'll do this, I'll do this, whoop, there's my quartic, just like that. Yeah, it's not going to be a big problem. How high can we go with the degree? Well, as high as we want. You know, you can go up to degree 99 if you want, but I'll say if we can do degree 5, we'll be like, okay, we can do any degree now. It'll just take a long time. So the weapons we use for degree 5 will be able to handle anything higher than as high as you want. There aren't really common names for high degree polynomials. Those ones we just did, the cubic, quartic, quintic, they have fancy names. After that, we just start calling them degree 42 or degree 18, whatever they are. But we'll spend most of our time with degree 5 or less. We won't get too carried away here as far as the degrees. Like I say, once we can do 5, we'll be in great shape to do any degree. I wonder how the coefficients affect the shape of the graph. I just showed you that with the demonstration I did. By changing the coefficients, you start getting more max and mins, and it moves up, moves down, does all sorts of stuff. What's that actually going to do? How do I do it and actually graph it myself? Well, that's what the whole chapter is about. Okay, I'm going to do this part a little faster because this is all review, I think. Now, that was, how many slides was that? That was 5.5 of the 8 slides. So the next slide and a half, pretty much review. I'll go pretty quick, but you let me know, okay? If I have to re-explain something. Turning points. When a function switches from increasing to decreasing or vice versa, we get a turning point. Turning points are higher or lower than all nearby points. Turning points are also known as local max and local min. Is good? That's supposed to be like 100% review. We did that in both chapter 1 and chapter 2. Other properties to describe polynomial functions. We might talk about the domain and range. We might talk about the zeros, the y-intercept, the absolute extreme values, the symmetry, the end behavior. And here's an example to review all those things if they've slipped back into the recesses of your mind. Here's a function that we're going to use to talk about. In fact, it might be exactly the function I used in one of the other PowerPoints in Chapter 1. This might be a complete 100% copy and paste review from Chapter 1, but let's go through it. Domain, any x value is possible, so domain is x element of reals. Range, any y value is possible, so the range is y element of reals. Zeros, okay, I can pick them off. I got to estimate them here. It looks like close to 4, farther than 3, maybe about 3.5. 0, and maybe like negative 3.5. Got to sort of estimate off the graph here. That's what the PowerPoint gets to, negative 3.5, 0, 3.5. Y-intercept, okay, where does it meet the y-axis? It meets at y equals 0. Intervals of increase, okay, a little bit more difficult. I'll slow down here a little bit. It's increasing over here before it gets to negative 2. And then it's increasing again after x equals 2. Those are the times when it's increasing. So the way we describe that is we said it's increasing for x less than negative 2 and for x greater than 2. And then in between there, between negative 2 and 2, it decreases. So I get the decrease between negative 2 and 2. I went back to the old notation here in this PowerPoint. If you're great with the new notation, I love it. But I go back to the old notation here to make sure that we're clear on what I'm saying there. Absolute max, this doesn't have an absolute max. It goes off to infinity on this side, and then it doesn't have an absolute min either. It goes straight down like that and off to negative infinity. There is a local max though, right there, negative 2 comma 4. So it's a local max point at negative 2 with a local max value of 4. And then there's a local min, x value 2, y value negative 4. And the symmetry of this thing is odd, since every negative x value gives the negative version of the y value. I'll do the end behavior and then we'll pause for questions, because I hope this is all it. It might not be perfectly fresh in your brain, but when you see it, you're like, okay, I do remember that. As the x values get large and positive, so do the y values. They get large and positive. Here's how we write that. As x goes to infinity, y goes to infinity. And the other way, as x goes to negative infinity, y goes to negative infinity. So I get that. Okay, that's pretty fast. On purpose. I don't want to bore you. What questions do you have about any of that stuff on there, on that example from, well, that's weeks ago now, from Chapter 1. Any questions on any of that? That's how period 2 felt too. They're like, oh yeah, well, I might not remember exactly every single detail there, but I remember the gist of all that stuff, so it should be pretty good. Okay, so this last slide, and it was split in period 2. Oh, note, we will look more closely at end behavior, zeros, and turning points in the next lesson. So if you're like, I guess I sort of remember end behavior, zeros, and turning points, boy, I'm going to beat it to death tomorrow. Oh boy, we're just going to go over this. The lesson's literally called end behavior, zeros, and turning points. That's what I'm going to talk about tomorrow. Okay, it was sort of split down the middle in period 2. Half the people thought they had seen most of this before, and half the people were really a little confused about everything I was doing here after the first example. So I'm going to teach it this time like you've never seen any of this finite difference stuff before. I'll mention previous grades, but I'll sort of teach it like you haven't seen it. Recall that the first differences of a linear function are equal. Here's the table of values for a linear function. And how you know it's linear from the table is that every time you go up an x value, the y value goes up by 5. That might be the definition of linear. If you want to go in a straight line, you've got to go up by the same amount every time. You think about a set of stairs. It's got to go up by the same amount every single time if those stairs are going to go in a straight line. Have you ever walked on a set of stairs that's missing one stair or something like that? And you fall? We had a deck at my, when I was growing up at my house, the top stair was like this. And everybody I knew came over, tripped on the top step. You're so used to those stairs being in the exact same spot. If it's not there, you do this weird step. Anyways, linear functions. Do you remember this from grade 9? We did a lot of this in grade 9. Yeah? The first difference is thing, not like a little arrow here, it was like a little triangle thing we'd build here. And all we did in grade 9 was we looked and we went, are they the same all the way down? If they were the same all the way down, we said it's linear. If they weren't the same all the way down, we'd say it wasn't linear. That's all we did in grade 9. Here's what you were supposed to do in grade 10. But again, with coronavirus and everything, it's one of those things that could easily have got skipped. So you run into a quadratic function and you try and do the test to see, is it linear? And you check, okay, 12 to negative 4, that goes down 16. Negative 4 to negative 14, that goes down 10. Negative 14 to negative 18, it goes down 4. Negative 18 to negative 16, up 2. And then negative 16 to negative 8, up 8. In grade 9, you would have looked at that and said, okay, they're not all equal. It's not linear. And that would have been the end of the story. In grade 10, you do the first differences, then you do the second differences. I want to rewind for a second and go, why is it called first differences? I first talked about what is it going up by. But if you really want to calculate them, look at, in this first example, 13 minus 8 is 5. 8 minus 3 is 5. You're always taking the lower value and subtracting the one above it to see how much it went up by. And it works over here. Negative 4 minus 12 is negative 16. Negative 14, subtract negative 4 is negative 10. So you're always just subtracting by the one above it. This is a quadratic. It's a parabola, so it doesn't go up by the same amount every time. But watch what happens when I do it again. This is called the second differences. Negative 10 subtract negative 16 is 6. Negative 4 subtract negative 10, 6. 2 subtract negative 4, 6. 8 subtract 2 is 6. So I get the same second differences when it's degree 2. Does this ring a bell from grade 10? It does. Okay, well that's good because sometimes it gets skipped over. Well, the pattern continues, as you can imagine. Degree 1, first difference is equal. Degree 2, second difference is equal. Here comes the table of values for a degree 3 function. The third differences should be equal. So I made a table of values for this degree 3. You can punch them all in and see if I did okay, punching them in. But I checked them to make sure I got the right y values. And when I do the first differences, I get all different first differences. And that would be the end. If I was a grade 9 question, I'd go, they're not all the same. It's not linear. In grade 10, you'd do it again to check if it was a quadratic. And you'd subtract them all and you'd say, nope, they're not all equal. So it's not a degree 2 function. It's not a quadratic. Now I'm telling you, if you want to do degree 3, do that third difference, subtract them all, and you'll see you'll get all the same things. And so it is a degree 3. And it works for any degrees. We don't torture you by going, oh, let's see if this is a degree 77 and make you do it 77 times because that's just crazy, 3 or maybe 4, I think, is the most you'll ever see in the homework, because we have to do this 3 or 4 times. It's just subtraction, though. Take each number and subtract the one above it. So in general, for a polynomial of degree n, the nth differences will be equal. And as we continue to study rates of change, we'll get a feel. This implies we'll know exactly why this is true. No, we'll get a feel for why this might be true. We won't exactly get to the bottom of it just yet. Is this slide okay? It's the only slide I'm sort of worried about. Everything else is sort of like, okay, no problem. Questions there?